Hey everybody, welcome to the final video in chapter 7, which means probably the final new video for Physics 11 for the year 2020. Kind of crazy. Thanks for sticking it out doing this online learning. I really appreciate it. I know it's not what all of us signed up for, but I think we've made it work, and I appreciate your willingness to be sitting down watching this right now. I really do. I'd way rather you be here with me at school. I'm at school making this video right now, but that's okay. We're making do. Today, in this video, we are going to talk about how mass and energy are really the same thing. There's an equation you can see on the screen, E equals mc squared. A really famous equation that Einstein came up with. Everybody's seen this before. And when people see this equation, it's actually very simple to use. We're going to try it out in a moment. People look at that and they go, whoa, that's serious science, right? Like that's for real, man. E equals mc squared. I don't understand that. So just to show you, I did a quick Google search, just science chalkboard on Google. And you get a bunch of pictures like this one here. And this one has a bunch of random stuff on it. But wouldn't you know, right in the middle, if you do a Google image search for science chalkboard, there it is, E equals mc squared. People in movies like to put that on chalkboards if there's some crazy mathematician going through all these wild equations that look super confusing. You will find E equals mc squared on that chalkboard. Now, the equation itself is really simple. It literally is saying that energy and mass are equivalent. They really are the same thing. And they're related by c squared, which is the speed of light squared. This equation is not saying that you need to make things go the speed of light in order to have energy and mass be the same. That c squared is simply just a constant, right? Just a number that we use. Now, I feel like I may have mentioned this before, I'm not sure. With this equation, energy and mass are equivalent. We know how, as humans, to tap in a little bit into taking mass and converting it into energy. And when I say we tap into it, we're actually relying on things being radioactive to do it for us. And we're going to get into some radioactivity in this video. But when things are radioactive, it turns out that energy of radiation, the thing that makes them dangerous, is actually because mass disappears. It's gone forever and it turns into energy. So the mass is being converted into energy. This equation, and Einstein said we should be able to take energy and convert it back into mass, but we haven't figured out how that works yet. We've never sort of observed it in nature. We've never harnessed that for sort of humans to use in some way. But we should be able to take energy and convert it into mass. A really weird thought, though, is when we take mass and we convert it into energy, that energy is typically heat energy, and then we can use it to heat things up. That's how atomic bombs or nuclear reactors work, is they make lots of heat, and then you can use that heat to either hurt people, or if it's a bomb, or heat up water if it's a nuclear reactor. But if you were able to take energy out of the universe and convert it into mass, it's a weird thought experiment. What would the mass be that's created from the energy? Like, would it make a proton or a neutron or an electron, or would it make like a cell phone or a granola bar? Like, what would it turn the energy into? We don't know the answer to that question because we've never seen it happen. We've never figured out how it works. But it should. And who knows, maybe in your lifetime we'll find an example of that. It'd be pretty cool. Let me show you, though, just E equals mc squared, this kind of scary looking equation, just how easy it is. So there's good old Albert Einstein. He came up with this equation. Let's see what he actually meant by it. So in this equation, E is just your energy measured in joules. M is your mass in kilograms, and you have to watch that. Sometimes we have it in grams. And then again, c squared, we're not talking about making things go the speed of light. It's just a constant. C obviously being the speed of light, 3 times 10 to the 8 meters per second. So one calculation for us with this, and that's it, is converting mass to energy. You can see I've put the double-headed arrow because it should be a double-headed arrow, but I guess as of today, that's the only way we know how to go. We do know how to or harness nature taking mass and converting it into energy. We don't actually know how to make it go the other way, but that's okay. Let's try this. Back to the Future. I don't know if anybody's a fan. One of the bits of garbage Doc puts in his DeLorean to power it is a banana peel. So I'd like us to try this equation, E equals mc squared, with a banana peel, mass 100 grams. If you could convert it into energy, and notice I'm saying if, we do not have machines that convert banana peels into energy, right? We can harness nature's ability to do this on a very small scale with radioactive decay, but we do not know how to just like make machines to throw garbage into to turn it into energy. But I want to try this out. Do catch that you're in grams, and you're going to have to convert into kilograms before you can get the correct value for energy produced. I want you to keep in mind while you're doing this calculation, and humor me and try it out on your calculator, because we don't know how to make this equation go the other way. We know how to convert mass into energy, but not energy back into mass. That means the banana peel, if we could turn it into energy, you'd never get it back. It would be, in effect, gone forever. And you're probably sitting there going, Heinrich, who cares? It's just a banana peel. Would actually be a really nice way to get rid of garbage, right? Things that we don't need. Radioactive waste itself, right? You could put it in these machines and just have it turn into energy. So these machines don't exist yet, but maybe they will one day. I'm sure there's people right now, as you're watching this video, somewhere on this planet working at converting things into energy, right? Making one of these machines. So if we plug that 100 grams in as kilograms into that equation, 0.1 times c squared, you get 9 times 10 to the 15 J for joules. It's a big number, right? 10 to the 15. That's a lot of zeros on there. But you might be looking at that going, yeah, okay, I don't understand what we could do with that number. Well, this is just for fun, but that is enough energy to do a couple of things. I did some calculations for you. You could, if you think about potential energy, MGH, you could lift a 7,000 kilogram roller coaster up 100 meters vertically. So that'd be a nice big hill, right, to start your roller coaster ride. You could lift a big roller coaster 100 meters vertically, 1.311 billion, I'm putting my pinky finger in my mouth there, 1.311 billion times. That's insane, right? That is like a roller coaster that just runs nonstop for generations. So if we had a machine where you could convert a banana peel into energy and you could somehow store that energy, that would be an issue too, right? Would be storing that energy. But if you could actually have multiple generations of a family just like live on a roller coaster where it just runs nonstop. Because 1.311 billion runs of a roller coaster is going to take a while. Now, some of you might be listening to this going, Heinrich, I don't do roller coasters, man, because it makes my hair all messy. My hair gets all tangled up, and then I have to wash it and condition it and put some more product in it, and then I have to straighten it. So maybe you're into your hair, not roller coasters so much. You could run a 1500 watt hair dryer. So that's the big kind that like make the lights dim and sometimes pop breakers in your house. You could run a 1500 watt hair dryer for 285,000 years nonstop. That's the hair dryer on 24/7. And you're sort of looking at these two facts going, wow, I like that, right? I like my hair. But that's kind of ridiculous too, right? Riding a roller coaster over 1 billion times, that's ridiculous. Running a hair dryer for 285,000 years, that's ridiculous. What could you do that would be useful, Mr. Heinrich, off of that banana peel? Okay, fine. I'll give in. What would something useful, more useful be with that banana peel? Well, how about running the city of Penticton electricity needs for 25 years, for a quarter century. You could do that on one banana peel. Now remember, we don't have machines that do this, right? Not yet anyways. But that single banana peel would run all of Penticton for 25 years. The potential with this equation equals mc squared. The potential with anything that has mass to turn into energy, it is unbelievable. The life on this planet would totally change if we had these machines that could, even if they were really, really inefficient, if we could throw garbage in them and have it turn into energy, we'd have so much energy we wouldn't know what to do with it. It would totally change life on this planet. So fingers crossed that we can come up with one of these machines, because it would be totally, totally wild. So we don't have magical machines that can convert mass into energy. So what is a real life application of this knowledge? And I had mentioned it's about sort of atomic bombs and nuclear reactors, right? Those are things that are useful to us, one in a bad way, I'll call it, one in a good way, because they're based on things that are radioactive. So naturally unstable isotopes in our environment. Let me show you how radioactive decay works. I wish I could go more into atomic bombs and nuclear reactors. We just don't have time, which is unfortunate. But they are basically these things called chain reactions. An atomic bomb is an uncontrolled chain reaction, uncontrolled radioactive decay, and a nuclear reactor, on the flip side, is a chain reaction that's controlled. So it's many, many radioactive decays, but we limit it in special ways. So radioactive decay occurs when versions of elements with different numbers of neutrons, that's what an isotope is. So we'll write this in, variations of elements with different number of neutrons. I'm sure there's some chemists watching this video, and you've probably talked about ions. Those are variations of elements with different numbers of electrons, which give them an overall charge. Here we're talking about elements with different numbers of neutrons. Some isotopes, sometimes when you get a weird mix of how many protons and neutrons are in the nucleus of an atom, they just become unstable. And when these when these isotopes become unstable, they kind of blow themselves apart. And some mass gets converted into energy, and that energy, you got to watch out, because that energy might be enough to cause cancer. But on the flip side, cure cancer, right? The world is so strange. So I want to show you the three types of radioactive decay. There's calculations with the first two, and then not even with the last one. So the kinds of radioactive decay we need to know. The first one is alpha decay. And alpha decay occurs when an unstable nucleus sort of blows itself apart and releases a high-speed helium nucleus. So what we're going to do is we're going to look at some quick calculations on how to figure out some different decay types. So we're going to look at this element here, which is americium or americium. I never really know how to say this. Americium, I think. So this is called americium 243. Now the top number, when we write in this notation, is something called the mass number. The top number gives you the number of protons and neutrons. So it's the mass number. It's the total of the heavy subatomic particles. And chemists in the room, I think, will know that the bottom number is just the number of protons. It's the atomic number. So that's just P for protons. Now, I'm going to flash or pull up a sheet that you're going to need to look at. It is called the isotope chart. Let me sort of open that up here. Hopefully you can see this. You're going to need to find this document in the All Resources folder, because I am going to start pulling some numbers off of this in just a moment. So you may want to pause the video and go open this document for yourself. Print it off if you want, or you can just stare at it, flip back and forth between it. That's fine too. Yeah, can you even, you'll be able to see most of that, sorry. Let's zoom out a little bit. Oh, slowly loading. Anyways, this is what the chart looks like. It'll load on your computer better than my old piece of junk here. So what we're going to do is we're going to talk about this alpha decay. Now, a helium nucleus, I guess you don't really need to memorize this because you could always just look it up. But an alpha particle, the symbol for alpha is kind of like a fish, right? Kind of a sideways A. So it looks like that. And the alpha particle is 4,2 He. That's a helium nucleus where it's got 2 protons and then another 2 neutrons for a total of 4 of the heavy subatomic particles. So that is always your alpha particle, a 4,2 He. So what we're going to do with this equation is we are going to figure out that if it is unstable, this americium 243, if it undergoes an alpha decay and releases a high-speed helium nucleus, what's left over? What else is left after that helium nucleus goes flying out of there? And this is actually a pretty darn easy game, I think. Really all you need to do is balance out the top numbers, the mass numbers, and the bottom numbers, the atomic numbers. So we simply play this game. 4 plus something equals 243. And you go, oh, okay, so that's 239. So the 2 numbers on top have to add to 243. And then we play the same game with the atomic numbers on the bottom. 2 plus something equals 95. Okay, that's got to be a 93. Right? They need to add to 95. And now your bottom number here, the 93, you can go look that up on your isotope chart to figure out what that element is. So I'm going to flip back to that chart. Hopefully you can see this. 93, there it is, atomic number. We are talking about neptunium, which is Np. So that number is going to go in to our sort of equation here. Actually, we got the number, it's the element. There we go, Np. So there's the first step with these questions, is we have to balance the reaction. Now, I mentioned that when things are radioactive, that some mass disappears into energy. So now what we're going to do is we're going to figure out how much mass disappeared when americium became unstable and blew itself apart into a helium and a neptunium, because it turns out that this side of the equation has less mass than that side. And you're like, well, where did the mass go? Doesn't the mass have to be the same? No, the mass actually disappeared. It turned into energy. So what we're going to find is, I simply usually call it missing mass. Its technical name is the mass defect. To defect sometimes means to lose. Now what we need to do to find the mass defect is start looking up the different masses on that isotope chart for these 3 different elements here. So hopefully, again, when I flip to the isotope chart you can see this, but let's go look up the mass of this americium 243. You do have to be a little bit careful because sometimes there's different isotopes on the chart. But americium is right there. And we need the mass. There's only the one isotope on there, 243, so that's good. We need to pull this number with all 6 decimal places. So the calculations we're going to do for this radioactive decay stuff, they're easy, but they're a bit tedious because this chart gives us 6 decimal places. So we're going to go 243,061,373. Two 43,061,373. Now what we're going to do is we're going to subtract the mass of the helium and the neptunium added together. So I'm going to show that addition in brackets because this is what I'm going to have to do on the calculator. So go back to the isotope chart. we need to find helium now, which is here. Hopefully you can see this. I apologize if it's being cut off a little bit. So there's helium. Now you'll notice there are two isotopes of helium. We want helium-4. So this is actually the number we're after. Don't pick the helium-3. So we want 4.002602. 602. And we can go back to the isotope chart to look up the mass of that Neptunium-239. So we are right there. There it is. So 239.052.932. Now let's grab our calculators and see what we get for an answer. So I get that number. You can see that I've typed it in with the brackets just like I wrote it down. I get 0.005839. 0.005839. Now, hopefully you're critically thinking right now and you're going, well, what are the units on that? Because it turns out it's not kilograms, right? Like one single molecule of americium or helium or something is not 243 kilograms or 4 kilograms. On that isotope chart, your masses are in this weird unit called atomic mass units. And that is right here. So it's actually this U, which stands for atomic mass units. And what we're going to do is we're going to take that missing mass, that mass defect of 0.005839 atomic mass units. And really what we want to do is we want to plug it into E equals mc squared. But before we can plug that amount of mass and figure out how much energy it's worth, just like we did for the banana peel, the first thing we'll have to do is we'll have to convert into kilograms. So in order to do that, we are simply going to multiply that number by this value right here, this 1.66 times 10 to the negative 27 kilograms. That's what you multiply atomic mass units by to get it into kilograms. So I'm going to take that number on my calculator, multiply by 1.66 times 10 to the negative 27. Again, we're doing this because E equals mc squared requires us to be in kilograms. We get that number, 9.69. I'm going to keep that number on my calculator, but we'll trim it down here when we write it. Let's go back to this page. So that was multiplied by 1.66 times 10 to the negative 27. And that gave us a mass defect, now it's in kilograms, of, I forget, 969. 9.69 times 10 to the negative 30 kilograms. Now again, what we're doing is we want to plug this into E equals mc squared. So we've now got the mass, right? That's done. We've got it in kilograms. Instead of writing out the whole equation, if it's okay with you guys, I'd actually just like to do this. Why don't we just take that number on our calculator and just show it like this? Let's multiply it by c squared because we've already got the mass sitting there. So I'm just going to show it like this. It's a little bit quicker. So I'm going to take that number and multiply by the speed of light squared. And you should be able to do that without brackets on your calculator. Looks like that number, 8.72 times 10 to the negative 13, J for joules. 72 times 10 to the negative 13, J for joules. Now, that number by itself is for just one reaction. It's unimpressive, right? The banana peel gave us 10 to the 15 joules, and this gives us 10 to the negative 13. So you're looking at that, and you're like, well, you can't lift a roller coaster or power Penticton or run a hairdryer. That's stupid. It's actually not. What's kind of crazy is even though that's not a lot of energy, it is enough energy to cause something called ionizing radiation. And ionizing radiation means that little helium particle, when it comes flying out of there with this much energy, 8.72 times 10 to the negative 13 joules, it does have enough energy to change your DNA, which means potentially cause cancer. So that's a little bit tricky, right? That's not good. Although it can cure cancer at the same time, which is kind of crazy. So that is alpha decay. Just putting this out there, if you wanted to protect yourself from alpha decay, it's actually pretty wimpy in terms of how far it penetrates into your body. That's what we look at in terms of danger levels with radioactive materials, is how far they can penetrate. You can block alpha decay just with paper. So if you're writing this down on a sheet of paper and you were concerned about something blasting your head with alpha radiation, if you're a conspiracy theorist or something, you could just wear a paper hat or wear a paper suit, and it would block all of the alpha radiation. So the second kind of radiation that we need to know is a beta decay. And a beta decay is not a high-speed helium nucleus anymore. Now we're looking at a high-speed electron. And the beta particle itself is this. We already know the symbol for beta. It's that kind of fancy B. And a beta decay, a high-speed electron, we actually give it this symbol. The mass number is 0 because it's not made out of any protons or neutrons. And we actually put an atomic number of -1. And I'll talk about why that's the case in a moment. And then we just put E for electron. So in this equation, we're going to balance it out to start. What's kind of cool is this neptunium, this is actually the leftover of the alpha decay from part 1. It turns out that neptunium itself is radioactive. And if I tell you it undergoes a beta decay, we can say, all right, let's balance this out. We know that has to be the beta particle. And now we simply need to balance out the mass numbers on top and the atomic numbers on the bottom on either side of the equation. So we can play this game. 0 plus something equals 239. Okay, that's ridiculously easy. That's 239. Now be a little bit careful here. -1 plus something equals 93. You're like, oh, -1. So that actually has to be a -94. So 94 plus -1 is 93. And then we can go to our isotope chart. We can ask ourselves, hey, what's atomic number 94? And it's here in the middle, it's plutonium, Pu. So that's going to be some plutonium. Now, why is the atomic number for this beta decay a -1? Well, it turns out what's kind of crazy in a beta decay is that it's actually a neutron in the nucleus of this neptunium-239 that becomes unstable and blows apart. And I don't know if they tell you this in chemistry class, but neutrons, a neutral charge, they're actually a fused proton and electron. Right? And you're like, okay, that makes sense. A positive and a negative would sort of fuse together and give you no overall charge. So one of the neutrons in the nucleus blows itself apart into both a proton and an electron. The electron goes flying away. So you don't have to put this in your notes, but it leaves, right? It goes flying away with some amount of energy that we're going to find in just a moment. But the proton sticks around. So that's why the atomic number here is increased by 1. Because the protons stuck around, we went from 93 protons to 94 protons, but we actually lost the electron. Now, let's go find the mass defect, or if you want to call it by a simpler name, the missing mass. I guess not that either name is difficult. The mass defect, the neptunium-239, we already wrote that down at some point. It's 239.2 what was it? 052932 932 minus. Now, you might assume that we play the same game that we did earlier for the alpha, where we add these two things together. We add the mass of the electron, we add the mass of the plutonium. It turns out in this equation, you never include the mass of the electron. And there's actually a reason for that. I'm going to explain it really quickly. This might be confusing. You could ask me about it in Zoom or just take my word for it. You don't ignore the mass of the electron because it's really small. You ignore the mass of the electron because this plutonium that's formed actually is missing an electron. It is a -1 charge. And you don't have to put this in your notes. So when you look up this mass on the isotope chart, that isotope chart is giving you the masses, not of ions, but just like regular old atoms with the full content of electrons. So what we should be doing, technically, is looking up the mass of this plutonium and stripping away the mass of one electron, and then adding the mass of an electron right there. But again, mathematically, right? Why would you take away the mass of an electron from this thing only to add the mass of an electron when you're looking right there? Why don't we just not include the mass of the electron? So that's why I say ignore. It's just to make life easy, to make the calculations easy. So ignore the mass of the electron. We really just need the mass of that plutonium-239. We can grab that on the isotope chart. It is right in between here. There it is. 239 052157. .052.157. And you can grab your calculator and see what you get for a number there. So there's the value I get, 7.75 times 10 to the negative 4. Your calculator may or may not be putting it in scientific notation. It's not a big deal. 7.75 times 10 to the negative 4. So there's how much mass has just disappeared. It's actually turned into energy. And remember, that's in atomic mass units. But those units aren't going to work for us. We want to convert that into kilograms. So we're going to multiply by that little conversion number, which is on the isotope chart. Right there. So let's multiply by 1.66 times 10 to the negative 27. Gives us that number, 1.29 times 10 to the negative 30. That's in kilograms. And really the end goal, remember, is E equals mc squared. So let's take that number, multiply by c squared, and that's going to tell us how many joules we've got. Multiplied by c squared. Looks like 1.16 times 10 to the negative 13. J for joules. Final answer. So that's how much in this beta decay. There's how much energy you get from that little electron when it goes flying away. Entirely unimpressive number, but it is also enough to cause ionizing radiation, which means it could potentially change your DNA and cause cancer. So you'd want to stay away from things under or releasing beta radiation. Now, it does penetrate a little bit further. It's a smaller particle. It goes further into your body. So if you were concerned about receiving a dose of beta radiation and you wanted to protect yourself, paper wouldn't do it anymore, but thin metal foil, like aluminum foil, would work great. So you can make a tinfoil hat or like a tinfoil suit or something like that. And then you'd be blocking not only the alpha, but you'd be blocking all of the beta as well. And the last type of decay is actually the most dangerous of all. That's a gamma decay. And gamma decay is a high energy photon. Now remember photons, we talked about those back like in the second day of this chapter, something like that, second video. with Einstein's thought experiment with the photon clock. A photon is really just like a little ball of energy, almost like a little ball of light. And what's really cool is if you look at this equation, let me make it a bit bigger for you. Whoa, that's really big, but that works. Notice that the top numbers for gamma are 0, 0, which means nothing changes in this equation. So because gamma doesn't actually produce a particle with any mass, there is no calculations for us to do here. We simply go from something that's high energy, that's what this little star denotes, that it's in a high energy or unstable state, and then it releases that energy as a little photon, and you want to stay out of the way of these things, these little gamma particles. So if you want to protect yourself, you don't have to write this down, you need many centimeters of lead and or concrete. So gamma decay in terms of penetrating power goes in one side of you and out the other. So if you want to protect yourself from it, you basically need a bunker. Who knows? Maybe some of you have one. And there are no calculations for us in this one, right? Because this is like radium. Is Ra radium? I don't even know. 88. Yeah, it is. Radium-226 becomes radium-226. There's an unstable version, and then it becomes a stable version by letting go of this little high energy photon. So that one's super cool. You don't have to worry about that. But I do want you to know how to do those alpha and beta decays. So the homework or the practice that I'd like you to try with this lesson, in the All Resources folder, you will see a document called Radioactive Decay. And it should be pretty darn easy. It's got one more alpha decay to try. So you can practice one more alpha, and then it's got one more beta. And you will also find in the All Resources folder that there is a radioactive decay key. So you can go and check your answers once you've tried those two and make sure it all worked out. There's the last bit of chapter 7. There's the last bit of physics 11. That's crazy. I'm sad. Well, you're probably very happy. So that's the course. Thank you very much for all of your effort with this online learning. I know it's been a crazy time, and I honestly do appreciate your dedication to the course and that you stuck with it and did tests for me and joined me in Zoom meetings and sent me emails and asked me questions. It is really fantastic. And you guys crushed life teaching it to yourself, basically. You're a very impressive crew. So give that a try. We will finish off the course with next week a review document and then the last chapter test with some wave stuff and the relativity alpha beta decay, and you're done. So hopefully we can touch base soon at the next Zoom meeting. You can ask me any questions that came up during this. Otherwise, fire me an email at some point this week or next week, check in, and keep your eyes peeled for the review and the test. Take care, folks.